So we wanted a differential equation for acceleration. We wanted to show the displacement equation is a wave function. The third one has to do with this result here that we got for x double dot. We've been doing it last week, do you remember? There's a relationship between this and velocity, right? Namely, it's the derivative of, now, who remembers what goes in there? Half v squared, right? Okay, so let's take this idea, right? If x double dot's that, then the derivative of half v squared should also be that. Okay. Now I'm going to need a little more space from over here. So this is 3. The differential equation, not for acceleration, but for velocity. Okay. Okay, so I'm going to start off with this same statement. This is the simple harmonic motion statement, okay? But instead of x double dot, I'm going to use this derivative, okay? So, and that's with respect to x, which is good, because the right-hand side is also with respect to x. Okay, so we're going to get a relationship here by integrating out. Now, like I said to you before, these ones here you can't actually quote, but you're going to get asked to show these, right? So pay attention as I go through these steps. This is what you're going to have to produce. If I integrate both sides with respect to x, I'm going to get half v squared over here. What am I going to get on the right-hand side? X with respect to x. So the power's going to go up, and I've got to divide by the power. Right? So I'm going to get minus n squared. There goes the power, up, and then I have to divide by the new power. So far, so good? Now I've integrated, so I'm going to need to remember the constant, so I'll slap the constant on there. I'll divide it by 2 because everything else is divided by 2 and peer pressure, that kind of thing. So there's our constant. Okay. Now, just have to go a little bit further here. If I multiply through, I'm going to get v squared is minus n squared x squared plus c. Okay. Now, usually when you get a constant here, right, a constant integration, we're going to have to get rid of it somehow. What could we use to get rid of it? Well, when we did exponential growth and decay, okay, we tended to use an initial condition, like t equals 0 and population equals some such number. Okay? But can you see why an initial condition isn't going to be a whole lot of use in this particular situation? Can you see? Because this equation has nothing to do with time, right? That's why it's the differential equation. Okay, it has to do with displacement. So, what do I have to do? I want to think about velocity and displacement and how they relate to each other. Okay, so simple harmonic motion. It looks like this, right? Now, depending on what kinds of coefficients we put on this, for instance, changing the amplitude and that kind of thing, the velocity of this is going to change all over the place. It might be quite fast like this, or it could be a slower sort of thing, right? So I'm not going to know the actual concrete value of the velocity at any particular point along the graph. Except there are some special places on this graph where I absolutely know what the velocity is. Even if I don't know anything about, what these numbers are. Okay? What are the special points where we know the velocity? We know at these extremities, right? At these extreme positions. Okay? Whatever kind of simple harmonic motion it is, we know that at those spots, the velocity should equal 0, right? So velocity should equal 0 when, now, what are those extreme positions? Well, based on what we've been talking about before, it's about where you reach the edges of your amplitude, right? So when x is equal to a, or minus a, as you can see, it doesn't matter because you're squared, so at both sides you're getting the same thing because velocity is 0 at both points. I can take this, and this I can substitute in. Nothing to do with time. Okay? So I'm going to put in 0 squared equals minus n squared a squared plus c. Okay? So if I just rearrange, this is what I've got. And this is important. This shows that this c hanging off the end here, it's not just any random number. It actually has to do with n. What does that define? N defines period, right? How quickly it's oscillating. And A is amplitude, right? So how far it goes, right? So if I rewrite this equation here based on what I know now, I could say v squared is equal to, and here's my constant on the end, okay? So just tidying up a little bit, factoring out this n squared, and that's a minus sign, so I guess I can put it afterwards. I'm going to get this result. Okay? So, for instance, they might ask you to prove that the velocity squared of some kind of particle that's moving is, 4 outside of 36 minus x squared. Now, what can you read off this? What can you read off it? Have a look. This corresponds to n squared. Okay, n squared. So, in this case, n would be 2. Right? So, the period would be pi, right? Seconds or minutes or whatever unit we're in. So, period would be pi, should say time units. Okay? In the same way, this 36, right, corresponds to my a squared. So I can read off here that amplitude should be 6. Right? That's the amplitude of motion. It's going to go between plus or minus 6. Okay? Right, now let me emphasize again. This first characteristic here is the most important one. Okay? They ask you to prove, sorry, I'll stand another way. They ask you to prove simple harmonic motion, that's the one you want to go for, okay? However, these results come up so often, I want you to be able to recognize them. Not so that you actually include them as a proof, but so you can see what they mean, and that these numbers don't catch you by surprise. You actually know what they refer to, okay?